Okay, hopefully you've watched the other two videos, just basically understanding sigma notation. And then the other video I had was properties of summation, all the properties that are included. And now we're going to actually do some examples. And then your homework tonight is going to be to do question 1 through 10 on the worksheet called Properties of Summation 5.2. Okay, now again, I would hopefully you got like a little sticky note of all the main summation properties. I think there's really 4 of them because the adding and subtracting I'm going to show you in a minute. I feel like that's understandable. But I've got my little sticky note. I'll kind of keep it up here. So the first one is the sum from k equals 1 to n of a constant 6. Okay, so that would be this first property. When you take the sum of a constant, it's just 6 times whatever that number happens to be. If it's 1 through 10, or if it's 2, whatever it happens to be. So you would just write 6n. Done. That's easy. All right. Now the next one is the sum of 5k squared. So let's see what we do about that. Well, remember, this 5 can actually be pulled out of the sum. So you can have 5 and then take the sum, k equals 1 to k squared. Now, if you look over here, there is a summation of k squared. That would be this one right here that I wrote in my little card. Now, I'm going to jump right to the fractions. So I'm going to replace this with the k squared summation, which is n cubed over 3 plus n squared over 2 plus n over 6. And I'm going to multiply all that by 5. So what would that be? It'll just be 5n cubed over 3 plus 5n squared over 2 plus 5n over 6. And that's it. And now we could make that n become, any number we want, 5. And if we put a 5 right there, and right here, we could actually get out a sum from k equals 1 to 5 of 5k squared. Very simple. All right, let's do another one. Move this down. Okay, so this one I am adding and subtracting some constants, some k values. So let's kind of break this apart. So really what you're doing here is you're going to sum all of this. Okay, I guess I should actually put this in parentheses. You're going to sum this. So you're going to almost take the sum of each one separately. So sum k equals 1 to n of 10 plus the sum k equals 1 to n of k minus, I'm going to kind of jump the gun. That 2 is kind of just like what we did above. I'm going to pull that 2 out. 2 times the sum k equals 1 to n of k cubed. And then I'm going to do each one of my properties based off of my little sticky note. So the sum of a constant is 10n. 10n. The constant times n. The sum of k would just be n squared over 2 plus n over 2. So plus n squared over 2 plus n over 2. Now this one you want to be careful. Remember, there's a 2 times this sum. So this would be minus 2 times, and then go to your k cubed one, which is down here. So this would be n to the 4th over 4 plus n to the 3rd over 2 plus n squared over 4. And you're going to distribute that negative 2 through. So let's see, what would that be? That would be negative n to the 4th over 2 minus just n cubed, right? Because those 2's would cancel. And then minus another 2n squared over 4, which would just be n squared over 2. And then, of course, you still have 10n plus the n squared over 2 plus the n over 2. And let's just look quick. We can clean this up. These are mathematical opposites. And I think that's it. So this is actually equivalent to 10n plus n over 2 minus n to the 4th over 2 minus n cubed. All right, now for the last example. All right, so what happens when I take the limit as n goes to infinity? What if this was going on and on and on forever and ever and ever? What's going to happen? I mean, we've worked a lot with limits, but your summation properties still hold, and then you work with the limits at the end, okay? So let's take this example, write this out for me. And this is actually one of your homework problems. This is number 7 on your worksheet tonight, so you're welcome. All right, so first thing I'm going to do is I'm going to rewrite this. The limit as n approaches infinity. And I'm going to, again, I don't want to say distribute, but take the sum of each of these, summation of each of these sums. So this would be the limit of the sum of k equals 1 to n of 12 over n plus the sum of k equals 1 to n of 16k squared over n cubed. Okay, now let's kind of talk about what this is going through. This is really 12 over some number n, okay? Some constant number. I can keep that 12 right there, and I can actually factor out this, I won't say factor out, but yes, factor out a 1 over n, because it really is just a constant that I'll multiply by the sum. And I can do that same thing over here, but I'm actually going to include the 16. Why didn't I include the 12 here? Because I just wanted to show you what happens when because you would have to actually rewrite it then as 1. But I'm going to keep this as just a 12. But over here, I'm going to actually factor out 16 and the n cubed. I keep saying factor out, but you almost rewrite it as a scalar. And then what would you have left? You'd have k squared. So again, what am I trying to do? I'm trying to make it look like my sticky note. Things from my sticky note. I'm trying to make it look like a constant or a k or a k squared or a k cubed. Okay? Now again, we're going to take the limit of this, but not just quite yet. We're going to kind of clean this up. All right, so how do we clean this up? Well, based off of Mr. Sticky Note, the sum of a constant would just be that constant times n. So I would just write this part right here as 12n. But I'm multiplying it by what I just took out before, 1 over n. Okay? So what would that be? Well, this would obviously reduce to 12. All right, now let's do it on this one right here, this piece. So plus 16 over n cubed. Now what is the sum of k squared? Okay, that's this one right here. So let me write this down for you. There you go, so you can see it. It's n cubed over 3. So times n cubed over 3 plus n squared over 2 plus n over 6. Now I'm going to distribute that through. It's a lot of fractions. You can do this. Okay, so what would I have? Well, 16 over n cubed times n cubed over 3 would just be 16 over 3. And 16 times n squared over 2 times the n cubed. Well, that fraction, again, you got to know your fractions, would reduce to 8 over an n. And then this would be 16n over 6n cubed. And what would that reduce to? 8 over 3n squared, I believe. Yes. Okay. Gosh, so what, again, are we doing here? I know this seems so complicated, but you'll see what happens at the end in a minute. So all I did is put this extra notation of limit as n goes to infinity, but you've done this part, okay? You try to make this look like a sticky note, either just a constant or just a k or just a k squared or just a k cubed. And you factor out the other n's and the numbers in front. This one I left the number. You could have factored out the 12 over n and then would have had n here, and then that would have canceled. Same thing, same concept. You would have had a 1, excuse me. But that's all I did. Okay, now look at what happens. Again, we're taking the limit as n approaches infinity. And now we go to our limit rules. What's the limit of a constant? Well, it's 12. What's the limit of another constant? Well, 16 over 3. What's the limit of an 8 over n as n approaches infinity? There's that rule again. We've written it so many times. What happens there? What happens there? That goes to 0. What about 8 over 3n squared? Oh, that also goes to 0. So your final answer is 12 plus 16 over 3, which is equal to 17 1/3. Okay? These are hard, but you can do them. You can. You've got to try them. Okay? This was probably the harder one. So try them out. All right? Complete, please, for me, 1 through 10 on that worksheet. Take a picture of it and send it to me. All right? Bye-bye.